Have you ever stopped to think about how software engineering itself well, changing? We seem to be moving beyond just front end, back end, even the classic full stack role.
Yeah, absolutely.
Today, we're going deep. We're exploring what feels like a new frontier, the full stack data systems engineer.
That's a great way to put it because this role, it isn't just about, coding a feature here or there. It's really about a holistic and end-to-end grasp of everything.
Everything, like from the user's screen.
Exactly.
Yeah.
From the browser through all the application layers right down into the nitty-gritty of the data infrastructure. Seeing that whole picture.
Okay, so this isn't just a new buzzword then. There are real reasons this is happening now.
Oh, definitely. Two big forces, really. First, businesses are finally seeing the huge advantage of letting one engineer or maybe a small tight-knit team actually own a feature.
Own it completely, like idea to production.
Precisely.
That-
Taking it all the way. It cuts down on those painful handoffs, the communication gaps between different specialized silos. It's just more efficient.
Makes sense. And the second force.
That's the tech side. It's the absolute explosion of microservices and cloud-native ways of building things.
Ah, right. So suddenly your app isn't one big thing, it's dozens, maybe hundreds of little pieces talking to each other.
Exactly. And when that happens, you have to get good at managing data across all those services, handling complex deployments, making sure the whole system stays up even if parts fail. It's a whole new ballgame.
Okay. So our mission for this deep dive then is to really unpack what this new converged skill set looks like.
Yeah, we want to give you the insights to understand what it really takes. Not just to build isolated bits, but to design, build, and operate the whole system, robust, scalable, ready for production.
Sounds ambitious. Where are we headed?
We'll start with some core architectural choices, then dive into the technologies for the app and data layers. We'll definitely need to cover the principles of distributed systems,
The tricky stuff.
the tricky but essential stuff. And then we'll tie it all together. Maybe look at a real-world example, like building a real-time user analytics platform from scratch.
Perfect. Let's dive in. All right, so let's properly define this full-stack data systems engineer. It definitely sounds like more than just, knowing a bit of front end and a bit of back end.
Oh, much more. The absolute key is that holistic understanding. It's about breaking down those traditional walls
So you could be tweaking CSS 1 minute.
and then diving deep into optimizing a Kafka pipeline or debugging a database query the next. It's that ability to move fluidly across the entire stack, understanding how a change in one place might ripple through the whole system.
Right, so the main objective isn't just getting something working. It's about building systems that are truly production ready, resilient, scalable from the get-go.
Exactly that. This role, it's a direct answer to those things we just talked about. Businesses want speed and ownership, which means end-to-end teams.
And the tech landscape, with microservices and cloud, demands engineers who get the distributed nature of both data and operations.
Precisely. It's about applying serious engineering discipline across that entire life cycle, not just in one narrow specialty.
Okay, so before you build anything, you've got that huge decision.
Right.
How do you structure it? Monolith or microservices? Feels like a classic debate.
It is, and it's crucial. It's not about which one is better universally. It's a strategic trade-off, like you said.
Let's start with the monolith, the single big application.
Right. Its big appeal, especially early on, is simplicity. If you've got a small team or you're building a prototype, a monolith can mean getting to market faster. Development, testing, deployment. It's all pretty straightforward initially. Think of it like an all-in-one kitchen gadget.
Okay, but like those gadgets, sometimes they do too much and get complicated. What are the downsides when a monolith grows?
They can become really cumbersome. Making a small change might mean understanding, testing, and redeploying the entire massive application. That slows things down.
And scaling.
Inefficient. If just one part, say user login, gets overloaded, you often have to scale the whole thing, compute, memory, everything. Plus, a single bug in one module can potentially bring down the entire application. And trying out new tech, forget it, or it's a major undertaking.
So the alternative is microservices, breaking it all down.
Exactly. You structure the application as a collection of small, independent services. Each one typically handles a specific business capability, has its own code base, maybe even its own database.
The big advantage there sounds like flexibility.
Immense flexibility. You can scale individual services based on their specific needs. Fault isolation is huge. If one service fails, it doesn't necessarily crash the whole system. Teams can work more independently, deploying their services on their own schedules. It can really accelerate development for specific features.
That sounds amazing, but I'm sensing a but coming. It can't be all sunshine and roses.
Definitely not. The trade-off is a significant jump in operational complexity. Suddenly you're managing dozens, maybe hundreds of deployed things.
Things like network calls between services, data consistency.
All of that. You need real expertise in DevOps, monitoring, distributed systems concepts. You're dealing with network latency, potential failures between services, making sure data stays consistent across multiple databases. It's like going from managing one big bus to coordinating a whole fleet of specialized delivery vans. Requires a different skill set.
So what if you're starting with a monolith, which many are, and want to move towards microservices? A big bang rewrite sounds terrifyingly risky.
It usually is. A much safer approach is often starting with a modular monolith. Build your monolith, but with really clear boundaries and well-defined interfaces between different logical parts inside it.
So it's easier to untangle later.
Exactly. And then you can employ patterns like the strangler fig pattern. It's a great analogy. You gradually strangle the old monolith by building new functionality as microservices around it.
How does that work in practice?
You might introduce an API gateway. It sits in front of everything. New requests for certain features get routed to your shiny new microservice. Requests for older features still go to the monolith. Over time, you card out more and more functionality until the monolith shrinks or even disappears. It de-risks the whole migration.
That's a really smart, iterative way to do it. So for you listening, when you're facing this monolith versus microservices decision, what are the key things to weigh up?
You really need to think about how complex is the system you're building inherently? How big is your team? And what's their experience level, especially with distributed systems? What are your scalability requirements, not just today, but down the road? How fast do you need to get to market? And critically, how much fault tolerance does this specific application require? There's no single right answer. It's all about context.
Okay, architecture decided. Now we get into the application layer itself. This is where you choose the tools for the visible parts and the logic behind them.
Right. Starting with the front end, the user interface. Key things you're looking for in a framework are usually component reusability, how modular it is, how it handles application state, and of course performance.
And the big players here are well known. Let's talk about React.
React's a hugely popular JavaScript library. Known for its flexibility, its core ideas are building UIs from reusable components and using a virtual DOM.
Explain the virtual DOM bit.
Sure, it's like a lightweight copy of the actual browser's UI kept in memory. When something changes, React updates this virtual copy first, compares it to the previous virtual copy, figures out the absolute minimum changes needed, and then updates the real browser DOM. It's very efficient, great for complex interactive UIs where lots of things might be changing.
Then you've got Angular, more of a full framework.
Exactly. Angular is a comprehensive, often described as opinionated framework. It typically uses TypeScript, has features like two-way data binding built in. It's often a strong choice for large enterprise-scale applications, maybe in finance or big corporations, where that structured, batteries-included approach is valued.
And Vue.js, kind of the middle ground.
Yeah, Vue often hits that sweet spot. It's known for being approachable, easy to learn, and you can adopt it progressively. Very popular with startups, single-page applications. It balances power and simplicity quite well.
And there are newer challengers making waves too, right? Like Svelte or Solid.js.
Definitely. Their approach is a bit different. They do more work at compile time. Instead of shipping a framework library to the browser, they compile your code down to highly optimized vanilla JavaScript. The promise is smaller bundle sizes and potentially faster runtime performance because the browser has less framework overhead to deal with. Exciting stuff happening there.
Okay, shifting to the back end, what drives the choices there? Node.js, Python, Java.
Key drivers are often the type of workload. Is your app mostly waiting for network or database responses, I/O bound, or is it doing heavy calculations, CPU bound? Your team's existing expertise is huge too, obviously. And the ecosystem around the language libraries, community support.
Let's run through some popular ones. Node.js.
Node.js, often with the Express.js framework, lets you use JavaScript across the full stack. It's fantastic for I/O-bound applications because of its non-blocking nature. Great for building scalable REST APIs, real-time systems using WebSockets, that kind of thing.
Python. We hear a lot about Django and Flask.
Right. Django is the batteries-included framework. It gives you an ORM, admin interface, lots of stuff out of the box. Great for complex, database-heavy web applications. Flask is the opposite of micro framework. Very minimalist, flexible, great for smaller apps, simple REST APIs, or maybe serving up machine learning models.
Enterprise world often means Java, right? Spring Boot.
Absolutely.
Yeah.
Java with Spring Boot is a powerhouse for enterprise-grade systems, highly scalable, very mature ecosystem, strong focus on reliability and security. You see it everywhere in banking, large SaaS platforms.
What about Ruby on Rails? Still relevant.
For sure. Rails built on Ruby has always prioritized developer happiness and convention over configuration. It's incredibly productive for getting MVPs, minimal viable products, out the door quickly. Still a great choice for rapid prototyping.
In the Microsoft world, ASP.NET Core.
Yep, ASP.NET Core runs on C#. It's cross-platform now, known for high performance, stability, very popular for building enterprise, web applications, APIs, portals. A really solid choice.
Okay, so you have your front end, your back end. They need to talk. The API is that contract. Let's compare the big two, REST and GraphQL.
This is a really important decision. REST, representational state transfer, has been the de facto standard for years. It uses standard HTTP verbs, get, d, post, put, delete, operates on resources, and is generally stateless.
Pros?
Simplicity, familiarity, huge adoption, works well with HTTP caching.
Cons?
The classic problems are overfetching. You get back way more data in the response than your specific UI component actually needs. And underfetching, you have to make multiple API calls to different endpoints to gather all the data for a single view. Versioning of REST APIs can also become quite painful over time.
And this is where GraphQL steps in.
Exactly. GraphQL is a query language for your API, typically served over a single endpoint. The client specifies exactly the data fields it needs in a query.
Solves the over-underfetching problem directly then.
Pretty much. The client gets precisely what it asked for, nothing more, nothing less, usually in a single request. This also largely eliminates the need for traditional API versioning, because clients just ask for the fields they know about. Plus, it has built-in support for real-time data updates via something called subscriptions.
What's the implication for developers? Does this change how front-end and back-end teams work?
It really can. GraphQL tends to empower front-end developers. They have more control and flexibility to fetch the exact data they need for new UI components without necessarily waiting for the back-end team to create a new specific endpoint. It can really accelerate UI development and foster more independence.
Okay, application layer covered. But where does all this data actually live? That brings us to data stores. SQL versus NoSQL.
Another fundamental choice with big implications. Let's start with SQL databases. The traditional relational databases like PostgreSQL, MySQL, SQL Server.
What defines them?
They use a structured data model with a predefined schema, think tables, rows, columns, with defined relationships between them. They generally scale vertically, meaning you make a single server more powerful, more CPU, RAM. Horizontal scaling, spreading data across multiple servers, is possible, but often more complex to set up and manage.
And their big strength is consistency.
Yes. They offer strong SAD guarantees. That stands for atomicity, consistency, isolation, durability. Basically, it ensures that transactions are processed reliably. Either the whole transaction completes successfully or it's rolled back entirely, keeping the data in a consistent state.
So when would you definitely reach for SQL?
You choose SQL when your data has clear, stable relationships that fit well into tables, and when that strong transactional integrity is absolutely paramount. Think financial systems, order processing in e-commerce, anywhere you really can't afford data inconsistencies.
Okay, now flip the coin. NoSQL databases. MongoDB, Cassandra, Redis, DynamoDB, a whole different world.
Totally different philosophy. NoSQL databases generally have flexible, dynamic schemas. Your data doesn't have to fit into predefined tables. You might have documents, key-value pairs, graph structures, wide columns, lots of variety.
And scaling is different, too.
Yes, they are typically designed for horizontal scaling from the ground up. You scale out by adding more commodity servers to a cluster. This makes them well-suited for handling massive amounts of data and very high traffic loads in distributed environments.
What about consistency? They trade AC for something else.
Often, yes. Many NoSQL databases offer what's called base consistency, basically available, soft state, eventually consistent. The focus shifts toward high availability and performance. Even if it means that for a brief period, different replicas of the data might not be perfectly in sync, they will eventually converge, though.
So when does NoSQL make more sense?
You'd lean towards NoSQL when your data is unstructured or semi-structured, or if the schema is likely to change rapidly. They excel when you need to handle huge volumes of data, require very high read-write throughput, and when availability and partition tolerance are perhaps more critical than immediate, strong consistency across the entire cluster. Think big data analytics, content management, social network feeds, real-time personalization.
It sounds like you might actually want both in a complex system.
Absolutely. That's becoming increasingly common, especially in microservices. It's called polyglot persistence. You don't have to pick just one database type for your entire application.
You choose the best tool for each job.
Exactly. You might use PostgreSQL for your core user accounts and orders because you need ACD guarantees. But maybe you use Redis for caching user sessions because it's incredibly fast. And perhaps a graph database like Neo4j for managing complex relationships like a social graph or recommendations. It's about leveraging the strengths of different database types within the same system.
All right, we've talked about architecture, applications, data stores. Let's get into the underlying principles that make these complex systems work, especially when they're distributed across many machines. The fundamentals of distributed systems.
This is where things get really fascinating and also quite challenging. First concept, scalability. How does your system handle increasing load?
We touched on this with SQL versus NoScale, vertical versus horizontal.
Right. Vertical scaling, scaling up, means adding more resources, CPU, RAM, disk, to a single machine. It's simpler conceptually, but you eventually hit physical limits, and high-end hardware gets very expensive.
So the modern approach is?
Horizontal scaling,
Yeah.
scaling out. You add more machines, servers, nodes to your system and distribute the load across them. This is the foundation of cloud computing. It's potentially limitless, much more cost-effective at scale, and inherently provides better fault tolerance.
Speaking of fault tolerance, systems fail, networks glitch, servers crash. How do you design for that?
That's fault tolerance and reliability. It's about anticipating failures and building mechanisms to handle them gracefully. Key techniques include redundancy, having standby components ready to take over immediately if an active one fails. Then there's replication, keeping multiple copies of your data on different nodes or even in different data centers. If one copy is lost or unavailable, others can serve requests.
And graceful degradation.
That means designing your system so that even if some non-critical parts fail, the core functionality continues to operate, perhaps with reduced performance or features. The system doesn't just fall over completely.
This sounds related to the famous CFP theorem. Can you break that down?
Sure, Brewer's CAP theorem is fundamental for distributed data stores. It states you can only simultaneously guarantee two out of these three properties: consistency, availability, and partition tolerance.
Okay, what do they mean in this context?
Consistency C means that all clients reading the data see the same, most up-to-date version, even immediately after a write. Availability A means that every request received by a non-failing node in the system must result in a response, though it might not be the absolute latest data. Partition tolerance, P, means the system continues to operate correctly even if network partitions occur, meaning messages get lost or delayed between nodes.
And the crucial point is?
The crucial point is that in any real-world distributed system that spans multiple servers or data centers, network partitions, P, are going to happen. You can't not have partition tolerance if you want a reliable system.
So you must choose P, which means the real trade-off is always between C and A during a partition.
Exactly. That's the core dilemma. During a network partition, does your system choose to remain consistent, a CP system, potentially by refusing writes or making parts of the system unavailable to avoid serving stale data? Or does it choose to remain available, an AP system, responding to all requests, even if it means some clients might read slightly stale data until the partition heals?
Can you give examples?
Traditional relational database clusters often lean towards CP. Systems like Amazon DynamoDB or Apache Cassandra are often cited as examples leaning towards AP, prioritizing availability. MongoDB can often be configured towards CP.
I've also heard of the pay-sell-LC theorem. How does that relate?
Pay-sell-C extends CKP. It says, if there is a partition, you trade between availability A and consistency. C, that's the CAP part. Else E, meaning during normal operation when there's no partition, you trade between latency L, how quickly you get a response, and consistency. Some systems might prioritize lower latency, even if it means slightly weaker consistency guarantees during normal times.
So consistency isn't just on or off. There's a spectrum.
Absolutely. There's a whole range of consistency models. At one end is strong consistency, like linearizability, which behaves as if there's only a single copy of the data, and operations happen instantaneously. Very strong guarantee, often harder to achieve with high performance. At the other end is eventual consistency, where if no new writes occur, all replicas will eventually converge to the same value. In between, you have models like read your writes, a user always sees their own updates, or monotonic reads, a user never sees data go backwards in time. Choosing the right model depends heavily on the application's requirements.
And how do all these distributed nodes actually agree on things, like who the leader is or the order of operations, especially when things might be failing?
That's the domain of consensus algorithms like Raft or Paxos. Their fundamental job is to allow a group of machines to agree on a single value or sequence of operations in a way that tolerates failures.
What kind of things do they handle?
Key aspects include things like leader election, reliably choosing one node to coordinate operations, and log replication, ensuring that all nodes agree on the same sequence of committed operations, which is critical for replicating state machines like databases or configuration stores in a fault-tolerant way.
Yeah.
These algorithms are complex but absolutely vital plumbing for reliable distributed systems.
Okay, building on those distributed systems principles, how do we actually make microservices resilient in practice? What are some common patterns engineers use to help them survive failures?
Great question. One foundational pattern is the API gateway. We mentioned it briefly with the Strangler fig.
Right, the single entry point.
Exactly. It acts as a front door for all incoming client requests, routing them to the appropriate backend microservice. But it does more than just routing. It's a perfect place to centralize common concerns. Things like authentication, authorization, rate limiting, SSL termination, caching. It simplifies the individual services and provides a single point of control and observation.
What about services finding each other? If instances are constantly coming and going, how does service A reliably call service B?
That's where service discovery comes in, often implemented using a service registry. Think of it like a dynamic phone book for your services.
How does it work?
When a new instance of a service starts up, it registers itself with the registry saying, here I am at this IP address and port, and I'm healthy. When another service needs to call it, it queries the registry. Give me the location of a healthy instance of service B. The registry provides it. This allows services to find each other dynamically, enabling easy scaling up or down and automatically routing around failed instances. Tools like Consul or Eureka or built-in features and orchestrators like Kubernetes handle this.
Okay, what about preventing one failing service from taking down others? Cascading failures sound bad.
They are. That's the job of the circuit breaker pattern. It's named after electrical circuit breakers.
How does it apply to software?
You wrap calls to potentially unreliable external services, like another microservice or a third-party API, in a circuit breaker component. This component monitors the calls. If the number of failures, timeouts, errors crosses a certain threshold within a time window, the circuit breaker trips or opens.
Meaning it stops making calls?
Exactly. For a configured period, any subsequent calls to that failing service are immediately rejected by the circuit breaker without even attempting the network call. This prevents the calling service from wasting resources trying to reach a dead service, protects the failing service from being overwhelmed while it tries to recover, and stops the failure from cascading upstream. After a timeout, the breaker might go into a half-open state, letting a few test calls through to see if the service has recovered.
That's clever. What about isolating resources within a service?
That's the bulkhead pattern. Imagine the watertight compartments on a ship. If one compartment floods, it doesn't sink the whole vessel.
So, applied to software.
You partition the resources. A service uses things like connection pools to databases, thread pools for handling requests based on the external dependencies they interact with. So if calls to service C suddenly slow down and start hogging threads, they only exhaust the threads allocated specifically for interacting with service C. Calls to service D, using a separate thread pool, remain unaffected. It contains the damage.
So these patterns, API gateway, service discovery, circuit breaker, bulkhead, they work together.
Absolutely. They're most effective as a combined strategy. They build multiple layers of defense against the inevitable failures in a complex distributed environment. They don't make failures impossible, but they drastically limit the impact or the blast radius when they do occur.
This is great theory. Let's try to make it concrete. Can we walk through an example? Say we need to build a real-time user analytics platform. How would these pieces fit together?
Perfect example.
Yeah.
Okay, the goal, track user actions on a website, clicks, page views, maybe scrolls in real time, aggregate that data and show live results on a dashboard. Classic full-stack data systems problem.
Where do we start? The front end, presumably.
Yep. For the dashboard itself, we'd likely use something like React to build a dynamic single-page application. SPA. It needs to display charts, key metrics, things that update live.
And how does it get those live updates? Polling.
Polling is an option, but for true real-time, WebSocket connections are better. The front end establishes a persistent WebSocket connection to the back end, allowing the server to push data updates instantly to the browser whenever new analytics are ready.
Okay, what about the back end? Where do user events go first?
We'd likely have a back-end API gateway, maybe built with Node.js. Its jobs would include serving the static files for the React app itself. It would also expose API endpoints, well, maybe a simple HTTP endpoint that the user's browser sends events to whenever they click or view a page.
And what does the gateway do with those raw events? Process them right there.
Probably not directly, especially if we expect high volume. A better approach is for the API gateway to act as a simple receiver and immediately forward those raw events into a message broker or queue. It also needs endpoints to serve the processed analytics data back to the React dashboard, either via those WebSockets or regular HTTP requests.
Okay, message broker, this sounds like a job for Apache Kafka.
Kafka is an excellent choice here for data ingestion. It acts as a durable, high-throughput buffer. The Node.js API gateway becomes a Kafka producer, sending every user interaction event into a Kafka topic.
Why the buffer? Why not process immediately?
Decoupling. Kafka decouples the event tracking, the quick API call from the browser, from the potentially more complex event processing. It can absorb huge traffic spikes without overwhelming the downstream processing system and without losing data, because Kafka is designed to be a distributed, partitioned, and replicated commit log. It provides durability.
So events are piling up in Kafka. How do we process them in real time?
We need a stream processing engine. Apache Spark Streaming is a powerful option. It can act as a Kafka consumer, reading batches of events from the Kafka topic in near real time.
What does Spark do with the events?
Using its structured streaming API, which treats streams like incrementally updated tables, Spark can perform stateful aggregations. For example, it could maintain running counts of page views per URL, calculate the number of unique active users in the last 5 minutes, things like that. It reads from Kafka, computes aggregates, and then needs to write those results somewhere.
Where do the aggregated results go? Back into Kafka?
Could go back to Kafka, but often a better choice for serving the dashboard is a database optimized for quick lookups. Let's say we use PostgreSQL for data storage of the aggregated results. Spark Streaming would write its calculated metrics, page views per minute, active user count, to tables in PostgreSQL.
And that's what the API gateway queries to feed the dashboard.
Exactly. The Node.js API gateway queries these aggregate tables in PostgreSQL to get the data needed to populate the charts and KPIs on the React front end, pushing updates via WebSockets.
Wow. Okay, so if you look at that whole flow.
You see a clear separation of concerns, right? React for visualization, Node.js gateway for ingestion API and serving results. Kafka as the durable ingestion buffer, Spark Streaming for the complex real-time aggregation logic, PostgreSQL as the serving layer database for the aggregates. Each component is playing to its strengths in that real-time data pipeline.
That really brings it together. But building all that on your laptop is one thing. How do you get this complex system running reliably in production? That sounds like a DevOps challenge.
It absolutely is. Getting to production reliably and managing it, there is a huge part of the data systems engineer role. The journey starts with containerization, almost always using Docker.
Packaging each piece.
Yep. You package your React app, or at least the web server serving it, your Node.js API gateway, your Spark Streaming application. Each gets bundled into its own Docker container with all its dependencies. This gives you portability. It runs the same way on a dev machine, in testing and production, and consistency.
But now you have all these containers. How do you manage them? Deploy them, scale them, make them talk to each other?
That's where orchestration comes in, and the dominant tool here is Kubernetes, often abbreviated K8s. Kubernetes automates the deployment, scaling, healing, and networking of containerized applications.
What are the key Kubernetes concepts we'd use here?
You'd define deployments to tell Kubernetes how many replicas, pods, which run your containers, of your Node.js gateway or Spark application you want running, and how to update them. You'd use services to give each deployment a stable internal IP address and DNS name, so other services, like the gateway needing to talk to the Spark results database, maybe also running in Kubernetes, can find it reliably, even as pods come and go. And you'd use config maps and secrets to inject configuration data and sensitive information, like API keys or database passwords, into your containers, keeping configuration separate from your container images.
Managing all those Kubernetes YAML files sounds like it could get complicated too.
It can. That's where tools like Helm come in. Helm is like a package manager for Kubernetes. It lets you bundle all the necessary Kubernetes resource definitions for an application, like our analytics platform, into a single package called a chart. These charts are versioned, templatable, making deployments much more repeatable and manageable. You can install, upgrade, or roll back your entire application stack with simple Helm commands.
And automating the whole build and deploy process?
That's continuous integration and continuous deployment, CI/CD, often implemented using GitOps principles these days. Your Git repository becomes the single source of truth, not just for your application code, but also for your infrastructure configuration, like the Helm charts or Kubernetes manifests.
How does the pipeline work?
When you push code changes to Git, a CI/CD pipeline, using tools like Jenkins, GitLab CI, GitHub Actions, automatically triggers. It builds your code, runs tests, builds new Docker images, pushes them to a registry, updates the image tags in your Helm chart or Kubernetes manifest, and then automatically triggers the deployment to your Kubernetes cluster. It makes the whole process fast, reliable, and auditable.
Okay, deployment is automated, but how do we know it's actually ready for production? What about testing this beast?
You need a multi-layered testing strategy. It's not enough just to test individual functions. You start with unit testing for small code components and integration testing for interactions between components within a service. AG, does my API route correctly call the database logic? For our example, maybe testing the Spark jobs logic in isolation, or testing its interaction with a mock Kafka or embedded PostgreSQL using libraries like test containers.
What about testing interactions between services?
That's where contract testing is valuable. Since services communicate via APIs like REST or Kafka messages, contract testing ensures that the consumer of an API, like our Node.js gateway reading from Spark's output DB, and the provider of that API, the Spark job writing to the DB or the schema it uses, agree on the format and structure of the contract. It catches breaking changes before they hit production. Tools like Pact are common here.
And testing the whole thing end to end.
Finally, yes, end-to-end E2E testing. This validates an entire user journey or data flow through the deployed system. For our analytics platform, an E2E test might simulate a user clicking on the website, check that the event flows through the API gateway into Kafka, gets processed by Spark, lands in PostgreSQL, and finally causes the dashboard metric to update.
That sounds hard to do reliably, especially with asynchronous stuff like Kafka and Spark.
It is challenging. You often need strategies like careful test data setup, maybe using dedicated test topics in Kafka, and techniques for correlating the input stimulus with the expected output, potentially involving message tracing or specific identifiers. It's complex, but gives the highest level of confidence.
Once it's running, how do you keep an eye on it? What happens when things go wrong?
You need full-stack observability. This is often described as having 3 pillars. The first is monitoring, primarily focused on metrics.
Numbers, like request rates.
Exactly. Time series, numerical data, things like API request latency and error rates, Kafka consumer lag, how far behind the stream processor is, Spark processing throughput and latency, database connection pool usage, CPU and memory utilization. Tools like Prometheus for collecting metrics and Grafana for visualizing them in dashboards are industry standards.
Pillar 2.
Logging. Collecting structured or unstructured log messages from all your services, React front-end, Node.js gateway, Spark jobs, databases, into a centralized logging system. Tools like the ELK stack, Elasticsearch, Logstash, Kibana, or Splunk allow you to search, analyze, and correlate logs across the entire system, which is invaluable for debugging problems.
And the third pillar.
Tracing, specifically distributed tracing. This is crucial for microservices. When a request comes into the API gateway and then fans out to multiple downstream services, tracing allows you to reconstruct the entire journey of that single request.
How?
It works by propagating a unique trace ID across service calls. Tools like Jaeger or OpenTelemetry collect timing and metadata for each step span within the trace. This lets you visualize the entire call graph for a request, see where time is being spent, and pinpoint bottlenecks or errors deep within the system. It's incredibly powerful for understanding complex interactions.
We can't forget security. What are the key considerations there?
Absolutely critical. It needs to be built in from the start. Key areas include encryption, using TLSSL to encrypt data in transit between services, and encrypting sensitive data at rest in databases or configuration files. Also crucial is authentication and authorization. Who are you and what are you allowed to do? This means securing access to things like Kafka topics, using mechanisms like SASL for authentication and ACLs for authorization, protecting your API gateway endpoints, using standards like OAuth 2.0 or JWT's JSON Web Tokens, and managing database credentials securely.
Lastly, performance isn't just about architecture, right? There's tuning involved.
Always. Performance tuning is an ongoing process. Once the system is running, you use your observability tool to identify bottlenecks and then tweak configuration parameters across the stack. For Kafka producers, you might adjust batch.size and linger.ms to trade off latency for throughput or enable compression. For Kafka brokers, tuning num.network.threads or num.io.threads. For Kafka consumers, adjusting fetch.min.bytes. For Spark streaming, configuring spark.default.parallelism, spark.sql.shuffle.partitions, maybe switching to a more efficient serializer like Cryo. It's about understanding the key knobs for each component and how they impact overall system performance based on your specific workload.
Wow, okay. That's a lot to cover. Let's try to wrap this deep dive up. What's the big picture takeaway here?
I think the main point is that becoming a full-stack data systems engineer is really about shifting perspective, moving beyond just focusing on one layer like the front end or the database to embracing a truly holistic view of the entire application lifecycle.
It's about mastering those architectural choices we talked about, really getting your head around distributed systems principles, and knowing how to build and operate these resilient, data-intensive pipelines from the browser all the way down to the storage.
Exactly. This convergence of skills, application development, data engineering, DevOps, distributed systems, thinking it isn't just some niche trend anymore. It feels like the new reality for building the kind of scalable, complex, data-driven applications that are becoming standard.
It really empowers engineers, doesn't it? Moves them from being specialists in just one part to being true owners of a capability.
It does. And that leads to a final thought, maybe something provocative for you to consider as you continue exploring this.
Lay it on us.
What new opportunities, but also what new challenges arise when a single engineer or a small team has the capability to truly own a feature end-to-end? From the pixels on the screen through the APIs, the stream processing, the machine learning models maybe, right down to the deepest data infrastructure.
That ability to close the loop on feedback, to iterate quickly, to solve problems across the entire stack.
Think about the potential speed of innovation that unlocks, the depth of problem solving possible when you're not constrained by silo boundaries. It's a pretty profound shift in capability.
That's a great point to ponder. So if people want to continue their own deep dive into this.
Oh, there's so much great material out there. Books like Martin Kleppmann's Designing Data-Intensive Applications are practically required reading. Online communities like the Data Engineering subreddit are full of practical discussions, exploring specific tech like Kafka, Spark, Kubernetes, and understanding distributed systems patterns. It's a continuous learning journey.
An exciting journey, though. It really feels like this is where modern software engineering is heading.
Absolutely. It's an incredibly exciting and impactful space to be working in right now.